Hey guys, thank you very much for checking my channel. So today I'm going to start the Apache Kafka series in English. So what I'm going to do in this series is I'm going to cover the in and out of Apache Kafka from scratch. So if there's anyone who is willing to learn Kafka or would like to work with Kafka, I hope this series would really benefit you guys. So today I'm going to start this series by onboarding you guys to some basic concepts like what is Apache Kafka, what are the components available in Kafka, what each of these components are doing, and so on. These concepts are very important for you if you would like to work with Kafka practically. So let us start learning Apache Kafka. So what is actually Apache Kafka? You could actually see tons of definitions available for Kafka on the internet. So I took one such definition here. So as per this definition, Apache Kafka is a distributed streaming message platform. In case you guys are not familiar with what is actually a distributed system or what is a streaming message platform, this definition could be really tricky for you to understand. So what I'm going to do is I'm going to split this entire sentence into two parts. First, we will see what is actually a distributed system, and then we will see what is actually a streaming message platform. So if we do like this, then it would be really easier for us to understand what is Apache Kafka all about, and then we can look deeper into the Kafka's architecture and so on. So first we will see why we are actually going for the concept of distributed systems. So let us assume that we have a single system like this, a simple computer system. And then we have an application like this, and this application is writing some data into the system. So this application might consist like three different processes as shown here. So imagine the Amazon website. So as you know, lot of customers all around the world would be doing shopping online, right? So what would actually happen in the backend is there will be an application like this, and this application will keep on writing all the customer transaction information into the Amazon system. So for example, like which customer bought what item, so information like this. So this whole situation will go fine without any kind of issues for some time. But once these applications start increasing, what will happen is the system might not be able to effectively handle all these processes at the same time. The reason is each system comes with a specific configuration. For example, the system shown here might be having like a specific CPU type, might be having like a 16 GB RAM and a 32 GB hard disk. So with this configuration or with this capability, it can handle all these blue processes effectively. But once this yellow processes starts writing into the system, it finds it very difficult to handle. To make it even more simple, imagine that you are playing a very high resolution video game on a laptop. At the same time, you parallelly connect an external hard disk on your laptop and start transferring huge files like in terms of gigabytes between a laptop and the hard disk. So basically, what is happening is two huge applications are running on your laptop, right? So what will happen is your laptop might hang at some point of time because it cannot handle those two huge applications. So the same thing is happening here. So this system is able to handle the blue processes, but once this yellow processes starts showing up, the system finds it very difficult to handle. So I hope now you got it. So what we can do here, one way would be like we can actually enhance the hardware of the system. For example, we can upgrade the CPU processor type, or we can increase the 16 GB RAM to 32 GB RAM, or we can even increase the hard disk of the system. So once we do like this, the system would then be able to handle this yellow process also. So we call this process of enhancing this hardware of the system as vertical scaling. But this vertical scaling is not a one-time solution. This whole situation might happen again and again. So just like these two yellow processes, now some red process might be showing up. So what we need to do is we need to do this vertical scaling again. But the problem is we cannot guarantee whether this vertical scaling would be an effective solution in 10 out of 10 cases. This is because even the best hardware available on the market today is not guaranteed to effectively handle all the scaling processes at the same time. Moreover, the cost for this vertical scaling is also very expensive because every time we actually upgrade the hardware of the system, right? So whether this vertical scaling is worth the cost that we are investing is always questionable. So we cannot really rely on this vertical scaling every time. So basically what is happening is whenever these applications are increasing or whenever they are scaling, this system is not equally scaling. So naturally we cannot build a scalable data pipeline between these applications and the system. So the problem associated with the single system or with the centralized system, we can also call this as a centralized system. The main problem is these systems are not scalable. The next disadvantage is, so now we have the system right, and all these processes are writing data into the system. So imagine this system now gets crashed. So now where all these processes will be writing the data? So they don't have a way to write the data anymore, right? So naturally, all these processes will also fail. Just like these processes, if there are like some other processes that are actually reading the data from this system, those processes will also fail because they don't have a way to read the data anymore. So naturally, all these processes are failing just because this system is not available. So the next disadvantage associated with the centralized system is these systems are not available. Similarly, this system has got crashed, right? But now we don't have a follow-up system to take its duty. We call it as a primary secondary setup. That is, whenever a primary system gets crashed, the secondary system takes the responsibility of the primary system and it continues to provide the service without any disruption. But here we don't have a setup like that. All we had is only one system, and that system also got crashed. So basically, the next disadvantage associated with the centralized system is these systems are not fault tolerant. Next, this system is crashed, and now assume that we restart the system. So upon restart, there are high chances that the data written by these processes into the system might got lost or might have got corrupted. If that's the case, then there is no way for us to recover those data because we have only one system and the data inside the system is no more. So the next disadvantage associated with the centralized system is these systems are not durable. One more important disadvantage would be, imagine that there are like 10 different processes requesting to read a particular data from this system at the same time. Okay, so if that's the case, it is not guaranteed that all those 10 processes can read the data at the same time. This is because this system is already busy handling all these write processes. So what might happen is 5 of those processes might be able to read the data and the remaining 5 processes might need to wait. Okay, so one important disadvantage with this centralized system is this system offers very low throughput. Okay, so this is very important disadvantage that we need to consider. So it is very obvious that we have so many disadvantages associated with the centralized system. So in order to overcome these advantages, we are actually moving from a centralized system towards the concept of distributed systems. So now I hope it is clear for you that why we are going towards the concept of distributed systems. So now we will see what is actually a distributed system and how a distributed system could overcome the problems associated with a centralized system that we just discussed. So now we have this system and there are processes that are writing data into the system. Okay. So now if this processes increases, previously what we did is we did vertical scaling, right? But with distributed technology, we won't do vertical scaling, but we perform horizontal scaling. That is, whenever the applications or the processes of these applications increases, we actually introduce new missions to our setup. Okay, so we call this process of adding new missions to the setup as horizontal scaling. So basically, a distributed system is a scalable system by means of horizontal scaling. So now if this system gets crashed, okay, what will happen is it will not affect the entire setup. Instead, another system from the setup will take the role of the system and provide the service without any kind of interruption. So distributed system is basically a fault tolerant system because there won't be any kind of downtime of the system. And also, since this new system takes the role of the crash system immediately, these processes that are writing the data, like these processes will not be affected also because the system is available immediately. So basically, a distributed system is also a very highly available system. Also, whenever these processes are writing data into the system, what will happen in distributed system is we also keep a copy of such data in other systems inside the setup as well. So imagine now we restart this crash system and come to know that the data inside the system got lost or got corrupted. So if that's the case, we can always recover the lost data from other systems inside this setup. So basically, a distributed system also serves the durability factor. Also, normally the distributed system provides a very high throughput. This is because in distributed system, each of the systems shown here don't work separately. Instead, they all work together as a cluster of resources. So imagine that there are like 10 applications requesting to read a particular data from the cluster. So previously, what I said in a centralized system is 5 of those applications will get the access immediately, while 5 of the remaining applications need to wait until everything gets completed, right? But in distributed system, one of the system will serve the 5 applications, while the remaining system, while the other system might serve the remaining 5 applications. So basically, none of the requesting applications will be blocked waiting for the resource. So that's the reason I said normally in a distributed system, the throughput will be very, very high. So now I hope you got what is actually a distributed system and why we actually need it. As I said already, if you want to understand Apache Kafka, you need to understand two terms. One is a distributed system and the other one is a streaming message platform. So now you understand what is actually a distributed system. So we'll proceed to the streaming message platform. So now we will see why we need a streaming platform or a message bus. So we have a single data pipeline as shown here. So this data pipeline extracts data from the source system and puts the data into the target system. The source might be a operational data store and the target might be a data warehouse system. So this is a very simple data pipeline. Now after some days, if there is one more target system extracting the data from the source, what you could already observe here is the load on the source system gets high, right? So the problem is as the number of targets keeps on increasing and continues extracting from the source system, the load on the source system keeps on increasing. So high load on the source system. So just like this, if there is one more source system from which the two target systems also extracts the data, what we observe is the load on the source system also gets increased. At the same time, the number of data pipelines also keeps on increasing. Also, there is some complexity in this practice. For example, assume that the source system stores the data in JSON format, but the target system stores the data in relational format. So what we need to do is we need to first extract the data, convert this data into relational format, and only then we can store the data into target. Similarly, if this target system accepts the data only in XML format, then we need to extract the data from the source, convert into XML format, and only then we can store the data in the target. So with increasing individual pipelines, the the data format complexities also keeps on increasing. So the problem with this practice is the data format complexities. So to overcome all these issues, we are actually moving towards the concept of message bus or streaming platform. So in case of a streaming platform, all the applications that writes data will actually connect into this common system. We call these applications as publishers. Similarly, all the applications that want to read the data will connect to this common system and then read the data. We call these applications as subscribers. So this is called actually streaming platform. That is, there will be a common platform like this and all the applications writing data will connect to this common platform and write the data. Similarly, all the applications that want to read the data will connect to this common platform and then read the data. So there is no more concept of individual target or source systems. All the applications actually communicate only to one platform. So this is all about the streaming platform. So now we saw what is a distributed system and then we also saw what is a message bus or a streaming platform. Now, try to imagine that instead of the single system in the common platform, what if we have multiple systems working in a distributed fashion? So this is what Apache Kafka all about. That is, Apache Kafka is a streaming message platform. At the same time, it works in a distributed fashion. So if you want to first know what is actually Apache Kafka all about, then you need to know what is a distributed system and then you need to know what is a streaming message platform and then you need to connect both these concepts together. So now I hope you would have got an idea of what is Apache Kafka all about. So this is very important for you to understand before we proceed further to discuss about the internals of Apache Kafka in detail. Let us now dive into Apache Kafka. Before looking into the architecture of Apache Kafka, I'll try to provide a very brief overview of Kafka. So Kafka is actually an open source technology developed at LinkedIn. This technology was then donated to Apache, which is a non-profit software foundation. One more interesting fact is the developers who developed Kafka at LinkedIn, so these guys came out of the company and then they started their own company called Confluent. So this company specializes in providing services surrounding Kafka. Also, Confluent is now one of the very successful company in this discipline. Kafka is actually written using Java and Scala. However, if you don't know these languages, you need not worry about that because there are support available for several clients for using Kafka like C++, Python, Ruby, and so on. I have provided a link in the description. So if you use that link, you can find the Kafka libraries available for such clients. Kafka can be used for several use cases. However, from a very high level, based on my opinion, you can aggregate all such use cases into two broad categories. One is Kafka can be used for building real-time data pipelines. So what is actually a real-time data pipeline? Imagine that you have a source system like an operational database and a target system like a data warehouse system. Now, whenever new data arrives at the source system, you might also need to reflect this data inside the data warehouse system for performing real-time analytics. Kafka can be used for building such applications. Next, Kafka can also be used for for building real-time streaming applications. So what is actually a stream? If you look Twitter for example, millions of tweets will be flowing every second, which means millions of data will be flowing every second, right? So this continuous flow of data is actually called a stream. So now what is actually a real-time streaming application? Imagine that you want to watch a movie in Netflix. So what you do is you log into Netflix and then type the movie that you want. For example, Inception. So once you finish watching the movie, you might notice that Netflix gives you some recommendation. For example, like Christopher Nolan's movies or DiCaprio's movies. Okay. So how this is happening? So how this is happening is, so when you give the input, that is when you type Inception, Netflix processes this message, this input, and then immediately gives you a recommendation based on the input that you provide. So this is actually called as real-time streaming application. So Apache Kafka can be used for building such real-time streaming applications. And Apache Kafka is being used at all these tech giant companies like LinkedIn, Netflix, Twitter, Apple, and so on. You can also find some interesting success stories that these companies have published on their website about using Kafka. Now, we will look into the Kafka architecture on a very high level. Basically, there are two important components in a Kafka architecture. The first one is called broker and the second one is called zookeeper. Brokers are actually the Kafka server applications. You can imagine each of these brokers as an individual computer system, and in each of these computer systems, a Kafka server application will be running. We call this Kafka server application as the broker application. These brokers actually store the application data. That is, if there is any application that is writing data to the Kafka, this means that these data are actually written to the brokers. As you see in the figure, these brokers also communicate among themselves. This means all these brokers work together as a cluster. We call this cluster as the Kafka cluster. Next to brokers, the most important component is Zookeeper. The Zookeeper is actually an external application. It is not a Kafka application. It runs outside the Kafka cluster. The main responsibility of this Zookeeper is to manage this Kafka cluster. That is, the brokers store the application data, whereas the Zookeeper stores the management data, that is the metadata. I will explain about Zookeeper in detail later in this video. Next, there should be some applications which write the data into this Kafka cluster, right? In Kafka, we call such applications as producers. So you could see two producers here. Also, the data that these producers write into Kafka are aggregated and stored under a logical concept called as topics. So what is actually a topic? You could imagine a topic as an equivalent to a table in a database. So if we have a database table named as customer, this means that this table might store customers information like his name, his phone number, so on. So similarly, if we have a Kafka topic named as customer, so this topic might contain customers personal information like his name, address, telephone number, and so on. So now I hope you understand what is actually a topic. So if you see here, the first producer is writing to two topics called topic A and topic B, and the second producer is writing to the topic C. So this means that a producer can write to one or more than one topics. Now if you look at these topics, you could see that each of these topics is having two copies. Topic A is stored in broker 0 and broker 1, topic B is stored in broker 0 and broker 2, and topic C is stored in broker 1 and broker 2. We call this as replication, that is, we replicate the topics across multiple brokers. So we have replicated topic A across broker broker 0 and broker 1. Now, we call all these applications writing data into the Kafka as producers, right? Similarly, we have applications that actually read the data from these Kafka topics. In Kafka, we call such applications as consumers. So, if you see here, the first consumer is actually reading from the topic A and topic B, and second consumer is reading from the topic C. So, a consumer can read from one or more than one topics. From the discussions that we made so far, you could already understand how Kafka actually satisfies the concept of a streaming message platform. Similarly, if you closely observe this architecture, you could also get an idea how Kafka satisfies the properties of a distributed system that we discussed earlier, like scalability, fault tolerance, and so on. I will explain it now. So you see these producer applications writing into these brokers, right? In case these producers applications keep on increasing, how we can scale Kafka? So we can scale Kafka by just adding more brokers. That is, we simply do the horizontal scaling. So Kafka is scalable. Also, now we have this producer C writing to the topic C, right? Suppose if this broker 1 gets crashed, what will happen? So this producer C will immediately start writing to the topic C available in broker 2. That is, this broker 2 will start taking the role of the broker 1. So literally there won't be any downtime in the Kafka system. Also, it keeps providing the service without any kind of interruption. So this means that Kafka is highly available, at the same time it is fault tolerant. So we saw that Kafka is highly scalable, available and fault tolerant, right? The next one is durability. So as I said, each topic here is having two copies. So in case the broker 1 gets crashed and after restart we come to know that the data belonging to topic C got corrupted, we can also recover the data from the broker 2 since the topic C is also available here. So naturally you can see that Kafka is also highly durable. The last one is throughput. The main reason why Apache Kafka is one of the leading streaming platform today is because of its very high performance. Basically, Kafka is able to provide such an high performance because of its scalability and also because of the way it actually organizes its data. However, I'm not going to speak about the data organization here. We will see about the Kafka data organization later in our Apache Kafka series. So now we could understand how Kafka satisfies all the properties that we discussed in the distributed systems. One more thing to be noted is here, we see three brokers here, right? We can call each of these brokers also as a node. So we have three nodes here. So we can call this entire Kafka cluster as a 3-node Kafka cluster. So now what we are going to do is, we have these components here, right? Like broker, consumer, producer. So we are going to see each of these components in detail. First, let us look into Kafka topics. As I said already, you can consider a Kafka topic as an equivalent to an entity or a table in a database system. For example, if you want to stream data related to a customer transaction system to Kafka, then you can think of creating Kafka topics like customer info, customer orders, and then stream the respective data to each of those topics. As you know, the data written by the producers are stored under these topics. So these data comprises of data units called as messages or records. Usually in Kafka, we call them as message. Finally, you cannot create two topics with the same name, just like how you cannot create two tables with the same name in a database. The next one is Kafka messages. As I just told, a Kafka message is nothing but a simple record stored under a topic. The structure of the Kafka message consists of a key value pair and a metadata. The key is completely optional. So it's up to the producer application whether to send or omit this key. But the value is mandatory. The value is normally considered as a Kafka message. For example, if there is a customer record that contains three fields like ID, name and phone number, we can consider each of these customer record as one Kafka message value. The metadata contains information about the Kafka message. For example, to which topic the Kafka message belongs to, at which time the Kafka message was produced to Kafka, and so on. Kafka messages are normally plain strings or simple bytes. They don't have a specific data type associated with them. For example, if a producer sends data in JSON format, this means that only the format of the data is in JSON but not the data type. So this is actually one of the beauty of Kafka, because if there is any consumer application that consumes these messages from Kafka, then they really need not worry about the data type of the Kafka messages. We identify each message stored in a topic by means of a concept called offset number, which is nothing but a simple integer value. For example, if there are 10 messages in a Kafka topic, then the first message might be having a offset value 0, the second message might be having a offset value 1, and so on. The next one is metadata. As I just said, the metadata contains information like to which topic the message belongs to, at which time the message was produced to Kafka. In addition to this, it also contains information like headers, partition number. So headers are optional information sent by the producer. For example, the producer the producer can include some information like to which team this producer application belongs to. So something like this. Partition number is something that we will see very shortly in this video. So this is an example of a message structure. So as you could see, we have key, value, headers, timestamp, topic name and partition number. So just to remind you, the key is completely optional, whereas the value is the actual application record. So this is an example of a typical Kafka message for the topic customers. So as you could see, this message is in JSON format, but you should remember that the type of the message is still a plain string. So these information like topic, timestamp, partition, these are like the metadata information. So this metadata information says like this message belongs to the topic customers and it was produced at this time and it belongs to the partition 0. You can ignore partition now. You will see what is partition very shortly. And this is the message value. So we have skipped the message key here. So it contains only the message value. So this message value says that this record belongs to a customer whose ID is 100 and whose name is Ajit. So you could now relate this message structure to the structure that we just saw. So why I'm repeating this again is there is a concept called key, right? And this key is optional. You should not confuse this key with the key of a database table where it is mandatory. The database table key is totally different from the message key. Next, we will see what are Kafka partitions. Partitions is one of the most important concepts in Kafka, so please pay more attention here. The reason why I'm stressing is because if you don't understand this concept well, then you would really find very difficult to understand several things once you start working with Apache Kafka. So here we have a 3-node Kafka cluster. We have 3 brokers, broker 0, broker 1 and broker 2. Normally, Kafka does not store all the data belonging to each topic under a single file. Instead, it divides a topic into a set of partitions and stores the data under such partitions. For example, if there is a topic A, while creating this topic, I will ask Kafka to create this topic with 2 partitions. Accordingly, Kafka will create 2 partitions for this topic A, P0 and P1. For this topic, one partition will be created in broker 0 and the other partition will be created in broker 1. Here we are using a 3-node Kafka cluster, right? That's the reason why Kafka distributes these partitions uniformly across the brokers. In case if we have only this broker in our Kafka cluster, then both these partitions P0 and P1 will be created in this broker 0. And both these partitions are completely distinct. That is, if a producer sends a message to this topic, the messages that are stored in this partition P0 will not be stored in this partition P1. Similarly, the messages that are stored in this partition P1 will not be stored in this partition P0. So partition is nothing but the unit of storage in Kafka. So why Kafka is actually doing this? That is, instead of storing all the topic messages under a single file, why Kafka is actually storing these messages under separate partitions? There are several reasons for this. The most important reason is unlimited scaling. You will get to know more about this unlimited scaling clearly when we discuss about consumers later in this video. Please remember that you need to read all the messages from each of these partitions P0 and P1 if you want to fully recover all the messages belonging to this whole topic A. In each of these partitions, the messages are stored in the exact order as they arrive. For example, if a producer sends 5 messages to this topic and 3 messages are stored in partition P0 and 2 messages are stored in partition P1, those 3 messages in P0 are stored in the exact order as they arrived at P0. Similarly, those 2 messages at P1 are stored in the exact order as they arrived at P1. Each message in each of these partitions are identified by means of offset number. What you should remember here is the offsets for those 3 messages in P0 might be 0, 1 and 2. Similarly, the offsets for those 2 messages in P1 might be 0 and 1. This means the offsets are actually tied to the individual partitions. So they won't be like 0, 1, 2, 3, 4 and 5 across all the messages. This means you cannot arrange the messages across all the partitions by means of the offset number. However, in most of the real-time use cases, this won't be needed. As far as you are able to arrange the messages of an individual partition in order by means of the offset number, it would be more than enough. However, in case you want to order all the messages across all the partitions in order, we saw each message will have a timestamp in its metadata, right? So you could simply use the timestamp and arrange the messages across all the partitions in order. So whenever we create a topic in Kafka, we need to specify certain parameters. The first one is the number of partitions. So here I have specified 2 partitions while I created this topic A. So accordingly, Kafka created this topic with 2 partitions P0 and P1. The next one is replication factor. Replication factor is nothing but the number of copies that we wish to have for each partition in a topic. Here I have specified the replication factor as 3, and that's the reason for each partition you could see Kafka creating 3 copies each. We call each of these copies of a partition as partition replica or simply as replica. So you could see P0 having 3 copies and also partition P1 having 3 copies. The next one is retention period. Retention period is the amount of time until which the data written by the producers to these partitions will be stored in Kafka. In Kafka, the default retention period is 7 days or 168 hours. So after this 7 days, the data older than those 7 days will be deleted from Kafka. Also, you need to remember that the replication factor that you specify while creating a topic in Kafka must be equal to or less than the number of brokers available in your Kafka cluster. So here we have 3 brokers, right? So you can have 3 copies for each partition. In case you specify the replication factor as 4 while creating this topic, then Kafka will report error. Next, you see for each partition, one of the copies, one of the replica is marked in pink while the other 2 replicas are marked in yellow. The reason is the ones that are marked in pink are called as partition leaders while the ones that are marked in yellow are called as partition followers. So if there is a producer writing data to this topic A, which means it is actually writing data to these partitions P0 and P1. But for each partition, we have 3 copies, right? So for partition P0, we have 3 copies, and for partition P1 also we have 3 copies. So the producer will actually write only to the partition leaders. So you could see this producer A writing only to this pink replicas, right? So the partition followers will get updated once this write operation is completed. So they get updated by means of this interbroker communication as you see here. This is also applicable to the consumers. That is, the consumer reads only from the partition leaders. So when the consumer reads from the partition P0, it reads from this replica. Similarly, whenever the consumer reads from the partition P1, it reads from this replica. In case if this broker fails, we will also lose the leader partition for partition P0, right? So what will happen is one of the replicas, one of these 2 replicas will now become the new partition leader, and then the producer A will continue to write to the replica that has become the new leader. So this is all about partition leader and follower. Next, we will see some important terminologies surrounding partitions and replicas. So here I am having a 3-node Kafka cluster with 3 brokers, broker 0, broker 1 and broker 2. Now I am creating a topic A with 3 partitions and I am specifying a replication factor of 3, which means each of these 3 partitions will be having 3 copies. So as you see, this topic A is having 3 partitions P0, P1 and P2, and each of these 3 partitions are having 3 copies or 3 replicas. What you need to note here is the ID of each of these replicas are equivalent to the broker IDs. That is, this replica with ID 0 for the partition P0 is created on the broker 0. This replica 1 for the partition P0 is created on the broker B1. So this is actually the concept of the replicas. The next one is ISR, that is in-sync replicas. So in-sync replicas means which of these replicas for each of these partitions are actually live and up to date without any crash. So here the in-sync replicas 0, 1, 2 means that all the replicas for this partition P0 are live and up to date and they are not crashed. And the next one is leader. So here 0 means for partition P0 the replica 0, that is the replica that is stored on broker 0 is the leader. Similarly, here the leader 2 for partition P2 means the replica 2, that is the replica for the partition P2 created on broker 2 is the leader for this partition. So if a producer sends data to this partition P2, it sends only to the partition that is stored in broker 2. And the remaining 2 replicas will be updated once the write operation on this replica 2 gets completed. As I said already, the replica ID is the same as the broker ID, and the producer will write only to the leader of a partition. All the remaining replicas of a partition will be updated once the write operation to the leader of the partition gets completed. Now we will see about Kafka brokers and controllers. I hope by this time you would have already got a clear outline about what is actually a Kafka broker. As I said earlier while discussing the Kafka architecture, a Kafka broker is actually a Kafka server application running inside a host machine. In case there are 3 brokers in a Kafka cluster, you can imagine each of these brokers as an individual computer system, and in each of these computer systems a Kafka server application called broker application will be running. We also call each broker as a node. Brokers store the actual application data written by the producers. This means all the Kafka topics are actually created inside these brokers. To be even more exact, all the partitions of the Kafka topics are actually created inside the brokers. All the brokers inside a Kafka cluster also communicate among one another. We refer this as inter-broker communication. Next, controllers. In every Kafka cluster, one of the brokers will be a controller. So what is actually a controller? Controllers are responsible for the partition administration. For example, Assume that a partition has 3 copies, that is 3 replicas. Then the controller decides among these 3 replicas which replica should be the leader for that partition. Also, if this leader replica gets lost because of a possible broker failure, then the controller decides among the remaining 2 replicas which replica should be elected as the new leader. Another example would be controller also tracks the state of each partition, that is whether the partition is a newly created partition or the partition is already online or the partition was online and then became offline or the partition got deleted and so on. Controllers are elected by the zookeeper, that is among all the brokers in a Kafka cluster, the zookeeper decides which broker should be the controller. Also, if this broker, that is the controller, gets lost or crashed, then the zookeeper elects the new controller among the remaining brokers. Now, we will discuss about zookeepers. Zookeeper is actually an application that runs outside of the Kafka cluster. You can also have more than one zookeeper. In this case, all the zookeepers work together as a cluster and we call this cluster as zookeeper cluster. For example, if there are 3 systems and you have a zookeeper application running in each of these 3 systems, then all these 3 systems work together as a zookeeper cluster. The number of zookeepers in a zookeeper cluster should always be an odd number. There are several reasons for this. Let us skip that discussion for now. I will explain about this in a separate video later in our Apache Kafka series. Zookeeper is mainly responsible for the metadata management of the Kafka cluster. For example, it tracks the state of the Kafka brokers, that is, which of the brokers are alive, which of the brokers are crashed and not part of the Kafka cluster anymore, and so on. Also, Zookeeper is responsible for alerting the controller among all the available brokers. Also, Zookeeper contains certain other metadata information. For example, list of all the Kafka topics in the Kafka cluster and the number of partitions for each topic. It also contains information about the location of all the replicas for each topic partition, and it also contains information about access control list. We will see about access control list in detail later in the Kafka series. For now, I will keep the discussion very simple. So access control list is nothing but a list that contains the list of accesses for each entity. For example, if there is a producer, then the access control list for this producer contains the information about all the topics to which the producer is authorized to write data. So this is just an example. Now we will see about producers. So as you know, producers are nothing but the publishers of data. That is, they are the applications that actually write the data to the Kafka topics. To make it even more simple, if there is a backend application that is writing data to a database system, you can consider this backend application as a producer. The next one is data publishing strategy. So what is actually a data publishing strategy? Assume that a producer is actually writing data to a topic and this topic consists of 3 partitions. Then there should be some mechanism that actually decides how the messages sent by the producer should be distributed among these 3 partitions. So we call this mechanism as data publishing strategy. There are certain rules for this data publishing strategy. Whenever a producer is writing data to a topic, it first checks the topic configuration. That is, how many partitions are available for this topic and what are the partition IDs. So the first rule is the producer explicitly specifies the partition ID in the message. So this message is stored in this partition. In case the producer does not specify the partition ID explicitly, then Kafka checks whether there is any key is present in the message that the producer sends. So if there is a key, then Kafka computes the hash function based on the key and the total number of partitions available for this topic and decides the partition ID, and this message will be stored in this partition. In case if there is no key present in the message and also if the producer does not specify any partition ID, then Kafka uses the default method, which is the round robin strategy. So round robin means assume that a topic has 3 partitions. So the first message that the producer sent will be stored in the first partition, second message will be stored in the second partition, third message will be stored in the third partition, and the cycle repeats. Once the partitions of a topic are assigned to the producers, then the producer actually writes the data to the partition leader. For example, if there is a partition P0 is assigned to this producer and if this partition has 3 replicas, then one of the replica will be the leader and the producer will write the data only to that leader. The remaining 2 replicas will be updated after the write operation is completed. The next one is Kafka consumers. Consumers are actually the applications that reads messages from the Kafka topics. Consumers are identified by means of a consumer group. So what is actually a consumer group? Imagine there is an application that wants to read messages from a topic. Now this application might trigger like 10 different consumers and all these consumers start reading from the topic at the same time. Now Kafka has to understand to which application all these 10 different consumers belongs to, right? So for this purpose, we use an identity called consumer group. Each consumer group can subscribe to any number of topics. So the total number of consumers in a consumer group should be less than or equal to the total number of partitions across all the topics to which it subscribes. So what does it mean? Imagine that we have a consumer group that subscribes to 2 different topics. Each of these topics has 5 partitions. So in total, we have like 10 partitions. Now, the total number of consumers in this consumer group should be less than or equal to 10. So this is the logic behind this concept. Technically speaking, what is actually a consumer? A consumer is nothing but an individual process doing some sort of activity. We can have several such processes running either on the same machine or on different machines. So once a consumer group subscribes to a topic, Kafka performs the assignment of partitions to each consumer. For example, if a consumer group has 2 consumers and it subscribes to a topic that has 2 partitions, then Kafka performs the assignment of each of these partitions to each of those 2 consumers in the consumer group. If the concept of consumers is still confusing for you, now you will get it clear. So now I have an example. In this example, I have a consumer group that subscribes to 2 topics, topic A and topic B. Topic A contains 3 partitions, PA0, PA1 and PA2. Topic B contains 2 partitions, PB0 and PB1. Now, if the total number of consumers in the consumer group is equal to the total number of partitions to which it subscribes, then what will happen is each of the consumer will be assigned a partition by Kafka and each of these consumers will start reading in parallel. While discussing the Kafka architecture, I mentioned a concept named unlimited scaling, right? So this is an example of unlimited scaling. That is, we can scale the number of consumers equal to the number of partitions to which our consumer group is subscribing. Since each of these partitions are distinct, that is, the messages available in the first partition will not be available in the second partition. So since each of these partitions are distinct, each of these consumers can start consuming in parallel without any disruption. This is one of the main reasons why Kafka is actually splitting a topic into a set of partitions instead of storing all the topic data under a single file. In case the total number of consumers in a consumer group is less than the total number of partitions, then what might happen is some of the consumers might be assigned more than one partitions. So in our case, what is happening here is PA0, PA1 and PA2 are assigned to the 3 consumers in order. Then PB0 and PB1 are assigned to C1 and C2 again respectively. So C1 is assigned 2 partitions and C2 is assigned 2 partitions. In case the total number of consumers is more than the total number of partitions available, then what will happen is each of these partitions will be assigned to one consumer and then the exceeding consumers will remain idle. So this is like wasting of resources, which we should definitely avoid doing it. Also, in all these 3 cases, you could notice one thing, that is, a single partition will never be assigned to more than one consumer inside a consumer group. So now I hope you understand the concept of consumers and how partitions are assigned to the consumers inside a consumer group. We have come to the end of the first video in our Apache Kafka series. So now I'll try to summarize what we saw today that is specifically related to Apache Kafka. So first, we saw about the Kafka architecture on a very high level. And then we saw about Kafka topics, Kafka messages, Kafka partitions. Followed by that, we also saw about Kafka brokers and controllers and also Kafka zookeepers. And finally, we saw about Kafka producers and Kafka consumers. We also saw the concept of consumers and how they work together inside a consumer group. In the next video, I'll explain how to set up Apache Kafka on your laptop and then start a simple producer and a consumer application and start writing and reading messages to and from Kafka. Also, in the subsequent videos, I'll try to explain many interesting things connected with Apache Kafka, like how to write a producer and consumer application using clients like Python, Scala, and also how to integrate big data applications with Apache Kafka, and so on. So in case you would like to learn these things, and if you like my video, please subscribe to my channel. So, thank you very much for watching, and I wish you all good luck in your Kafka journey.